So when a planet is formed, a great amount of energy is released, and this energy, this process is referred to as accretion. Accretion is the act of taking, let's say, a bunch of tiny planetesimals and letting them gravitationally collapse to form a larger object here, a planet. So let's take a look at the energy balance. We can write the potential energy U as 3/5 multiplied by g times m squared divided by r. So these variables, g is the gravitational constant, not the acceleration due to gravity, but the gravitational constant itself. M is the mass, so m is the total mass of the system. Notice that there's no term here for how many particles or how many planetesimals are coming together. We can have two large fellows coming to make a larger mass, or we can divide it up into three things that are coming together to make the same kind of mass, or lots of tiny objects, maybe an uncountable number to make the same size mass. But if this mass is the same as this one, is the same as this one, the total amount of energy is the same, so long as all of the little bits and pieces that come together to form this larger planetary object all come together all at the same time. And then r is the radius of the object that we make. So we can write U, the potential energy. We want to add a temperature term here. Can be written as the heat capacity multiplied by the mass multiplied by the temperature change. This is what we're really interested in here for our purposes. How much of a temperature increase is there from this accretional energy? And so if U is equal to these things, we can make this substitution into here. So the heat capacity multiplied by mass multiplied by delta T is equal to 3/5 times G times m squared divided by R. So with a little manipulation, we get delta T is equal to 3/5 times G times m divided by R times Cp, which is, again, the heat capacity. So this is the equation we're going to use. We're going to use this guy here and take a look at Earth as an example. How hot would the temperature be? What kind of delta T or temperature increase would we have if we accrete the Earth? Well, we need a couple of constants here. We will use G, the gravitational constant, a universal constant, 6.67 times 10 to the minus 11, and that is in units of meters cubed divided by kilograms times seconds squared. Then we have m, the total mass of the Earth, and that is about 5.972 multiplied by 10 to the 24 kilograms. And then we will have the radius of the Earth, which, well, we have meters here, so we'll just put this in meters. 6,371 kilometers, or for meters, we'll just add 3 zeros, so that we're keeping our units in kilograms and meters. And then we will look for a heat capacity that is representative of Earth materials as a whole, and we'll use 1,000 joules per Kelvin dot kilogram, again using units of kilogram. So let's put all this into the delta T equation. So we said that delta T is equal to 3/5 times G times M divided by R times Cp. So delta T is equal to 6.674 times 10 to the minus 11. We'll insert the units later. This is multiplied by 5.972 times 10 to the 24. And then this whole thing is divided by 6,371 with 3 zeros, and then 1,000. And the number we get is 37,513 Kelvin. Now that is a very, very large temperature. It is a maximum temperature. Remember, we are assuming here that all of the bits and pieces that form Earth all come together at precisely the same time. If they come in slowly, then we'd accrete the same amount of energy, but some of that energy would be lost in the process. So we wouldn't necessarily have all of that energy coming in at once. But if we did have it all coming in at once, we'd have enough of a temperature increase to melt the Earth several times over. Let's do a simple check to make sure that the units work out. For space, we'll need to erase the chalkboard. Remember, we have 3/5. This is delta T is equal to G times M divided by R times CP. Our units for G, we don't care about that. Those are unitless. So the units for G are meters cubed divided by kilograms times seconds squared. So that's RG. Our units for mass, we used kilograms, so there's M. And then we're dividing by radius, so that is 1 over, we used meters, so that's our 1 over R term here. And then we're going to multiply by 1 over CP. And our CP, CP is in joules per K dot kilogram. And so joules is in units of kilograms meters squared per second squared, and CP is equal to joules per K dot kilogram, that's K for kelvins. Then our units over here are going to be K times kilograms divided by joules. So this is our 1 over CP term right there. And then for joules, we're going to break that out into kilograms meters squared divided by seconds squared. Since it's in the denominator here, we can cross out joules and just multiply by the inverse, which would be seconds squared divided by kilograms times meters squared. So let's see if everything cancels out. We have seconds squared here and seconds squared here. So far, so good. Kilograms and kilograms. We've got meters squared and a meter, so that's meters cubed. Cancels out this. Kilograms and kilograms, and that leaves us just with Kelvin. So the units work out. If we use the units as indicated, where we used kilograms, meters, and joules, then we would have a delta temperature that would be in units of kelvins. So the fun part about this kind of calculation is we can determine the total heating of the mass of any planetary object, again with this simplifying assumption that all of the masses come together at the exact same time. That would always be a maximum estimate for the total amount of heating, because if the masses come in slowly, we'll still create the same amount of energy, but we won't necessarily have the same amount of delta T heating, because some of that heat might be dissipated by radiation or conduction or convection as the planet grows and cools.